Good morning. We're going to be looking at 6.6. I wanted to show you my pie shirt. Pumpkin pie makes me happy. And here we go. 6.6 is exponential equations and change of base. The change of base formula is for people who don't have a calculator that has the log any base key. And so we've been using, this is the first section of chapter 6 that the author thought that you would use a calculator. All of the other sections, he thought you would do it completely by hand. And so now he wants to show you how to use your calculator. And of course, we started using our calculator from the beginning, and people with a change of base key were able to do it. I also showed you how to use this is any base key, and then the log key, this is log base 10, and then the ln key, that's log base e. And so I showed you how to use the change of base formula in a previous video, but I'm going to show you again because I just wanted you to be able to use your calculator early as well. And so anyway, so this is the change of base formula for any appropriate logarithm bases a and b. So I have log base b here and log base a there and log base a there, and it says appropriate for the base. And the base is not allowed to be negative, and so it must be positive, and not allowed to equal 1. And so they're not saying that this would be okay or true if you used an inappropriate base. So only if you use an appropriate base would it be true. And then for any input m that's appropriate. Appropriate means that it's non-negative, because the input has to be positive on a logarithm as well. And so log base b of m equals whatever new base you would like to use, log base a of m divided by log base a of b. Now the bases that would be good to use are the bases that are on your calculator, right? And so if you don't have the any base key on your calculator, so this is not a discussion for you because you can just put in whatever base you want. You don't have to use the change of base formula. It's totally not necessary because you can put in any base you want. But if you only have the log key or you only have the natural log key, then those are the base you would want to use. This is base 10 and that's base e. So let's put that here. So this is base 10 would be good and base e would be good. And so how it'll look, log base 10, right, of some value, I don't know, whatever input you have, will equal just simply log of whatever input that you're putting in. And then for log base e, so log base e of whatever input equals just simply natural log of whatever input that you're trying to put in. So if you have a Casio calculator, then it's silly for you to even know the change of base formula. It's not necessary at all. I mean, it's okay for you to know it. Knowledge is always good, but it's not necessary. So if you have a Casio calculator, how you do this is the same as what you did. And so log base 6 of 37, I'm trying to get both of these on the screen at the same time. You hit this key if you have if you have a calculator that allows you to do any base of 37, hit equals, and it does it. It says here to round to 4 places, so I want to make sure that I show you how to round to 4 places. So this is 2.0152. That's 4 places. And then the next number is a 9. So this tells me to take that last number, which is a 2, because this is a 9, and bump it up to 3. So I would write as my answer 2.0153 would be my answer. Okay. Now, if my calculator did not have this key that allowed me to choose any base I wanted, then what I'm going to have to do is I'm going to have to use either the log key or the natural log key. And I want to show you how to do that so that you can do it on your TI. I apologize, I don't have a TI here at home, and so I can't make a video with the TI. But if you bring your TI to my office hours or to my or to class, I'll show you how to use it. Okay, so log base 6 of 37. If you're going to make this into log base 10, then this would be log base 10. And I go up like this, log base 10 of 37. And then I draw my line down like this, log base 10 of 6. And the reason it works so well with the log is usually when it's base 10, you don't write a 10. You just leave it as just log 37 over log 6. So if you do that, log 37, right, up here in the top, and log 6 down in the bottom, see how the log kind of goes with the 37 and the log 6. And so that's my way of remembering the change of base formula. And then how you would put it in your calculator. So if your calculator allows you to have a fraction, then you would want to put in there log 37. You have to end the parenthesis and log 36, 6, and hit equals. And you notice you get exactly the same answer as that we got over here. I didn't expect to get a different answer. It's just a different way of putting it in the calculator to make it do it, so that when the calculator doesn't have the any base key. And so, but this calculator does have the any base key. So we get exactly the same answer. I want to show you that if you put it in using the division key, so log 37 divided by and then log 6, if you just hit the division key, it also work. And that's a lot of what your TIs only have. So log 37, this one opens a parenthesis, so I still have to close it. If yours doesn't open a parenthesis, then you don't need to close it. And then log 6, and so I need to close it. And I just did the divided, just using the divided, and I get exactly the same answer. Now, not all of the calculators have the log key. Some of them only have the natural log key. So if yours only has the natural log key, then you would be doing natural log of 37 divided by natural log of 6. And yes, that's going to be exactly the same answer, believe it or not. That's the change of base formula. So I'm going to use the fraction key, natural log of 37. I'm not writing down the answer over and over because it's the same answer, natural log of 6. And you get the same answer that we already had here. And you would get the same answer even if you did natural log of 37 and then did it with the divide, natural log of 6. So if your calculator doesn't have the fraction key, then you can do the divide. Okay, so that's exactly the same as how you would put this in here. So of course, this calculator that I'm using does have the any base key, and this is having pi as the base. So when I hit the log and I want pi, and pi is down here on the bottom is where it is, and it's in the mustard yellow color. So I have to hit the shift and then pi, and then I get the pi on my screen. So log base pi of 100, and I get 4.0229. There's 4 decimal places. That's what it's saying. Sometimes the directions say 3, and sometimes the directions say to the 10th. And so if they'd said 3, then I would have just done 3, but they said 4. The next number here was a 3, so I don't bump the 9 up, I leave it because this is a number under 5. So my answer is 4.0229. And of course, you can put this in your calculator, log base pi of 100. So you can put it in your calculator, log of 100 over log of pi. If your calculator doesn't have pi, you can use 3.1 pi, right, is equal to 3.14159. And I think that you should take at least that many digits to be accurate. And so hopefully your calculator has pi on there, but you'll find it if you look. So log of 100 divided by log of pi gives me exactly the same answer. You can't mix and match. So it's not going to be equal if I do log of 100 divided by natural log of pi. So you can't mix and match. It has to be the same top and bottom. And it could be any base. And so there's no reason to do base 2. But if you had a calculator that was a computer calculator or whatever have you, it might have base 2 on it. I don't know of a calculator that has base 2 on it, but there's some things that have base 2, and so you could because I think binary is base 2, and so a lot of no, I might be putting two things together. But if you had a different base, you could use any base, but you have to use the same base top and bottom. Okay, we did a lovely job on that. And then here they're asking us to solve some exponential problems. And the key is that they have to be in this exponential form in order to solve them. And that form is b raised to the x equals k. If you want it in words, it's a base raised to an exponent equals a result, and where each of these things are one piece is all they are. They're one piece, and so, or can be treated as one piece. And so you need to put it in the form. And then once you put it in the form, if you don't know the answer, if you know the answer, I mean, sometimes you put it in the form. There was one that you guys had on the lab, which was 3 times 5 to the x equals 15, if I'm remembering right. And that's not of the form because it has the base, which is 5, the exponent, which is x, and it has the 15, which is the result, but this 3 is extra. And so you need to get rid of the 3. Because it's multiplied by 3, you divide by 3. And when I divide by 3, I get 5 to the x equals 5. And so I don't need anything more to solve this because I know that the x is equal to 1. And so that's why I say put it in log form, but put it only in log form if you don't know what the answer is from that point. And so when you put it in log form, then you solve normally. And if appropriate, you can use your calculator to find an approximate solution. So that's kind of the story. There's 2 ways that you can handle it. If your calculator doesn't do base 2, because that's what this one is going to have, if you put it in log form, then you can take the log of both sides, or you can take the natural log of both sides. I'll show you that. This is for people who don't have a calculator that will do base 2, and so that'll do any base. So this one is of the form. I have the base, which is 2. I have the exponent, which is x minus 1, right? And I have the 8. So each of these pieces, the 2 is one piece, the x minus 1, I know that you're saying that's a binomial, but it's one exponent, so that's why I want to treat it like one piece, and then the 8 over here, right? So I just want to show you that, hey, this is all of those pieces. Then what I want to do is I want to write it, if you have a Casio calculator, in log form. Now, how it looks to write this in log form is you write I'm going to write it right here below. I wish I wouldn't have. I'll put it out here, over here in log form. So I have my base raised to my exponent equals my result. And so this is going to be my exponent equals my logarithm to my base, and my input is my result. That's in logarithm form. So in this case, my exponent is x minus 1, and so I'm going to write down x minus 1, and then I need to put my logarithm, so log, and my log needs a base, and the base is 2, and so I put my 2 down here. And then my result up here, right? My result was 8. And so that's my input is 8. Now the good news is the calculator will do this, log base 2 of 8. And this one actually is a nice number. And so if it's not a nice number, then I wait. And so I'm just going to show you that it is a nice number, and I'll show you what to do when it's not a nice number, but this one is a nice number. So log base 2 of 8, and it's a nice number. It's the nice number 3. That's the nice number it is. So if it was a number that filled my screen, then I would just leave it here in this form until I round at the end. But since it's a nice number, it's okay for me to just put 3. So this is x minus 1 equals 3. And remember, I was trying to solve for x, so I would add 1 to both sides, and I get x is 4. So it says to solve, and when appropriate, and include an approximation to 3 decimal places. Now this one, the answer is just 4. And so it's not appropriate to include a decimal to 3 places. So it says, when appropriate, do that. So if it comes out nice, then don't do that. Now this came out nice, but if it had been, 2, and it had been, instead of the input had been not 8, but had been 9. So I'm going to get up there and put 9 in there. Then you see that it fills your screen with numbers. And then that's when we're going to give an exact answer and an approximate answer. I'll show you how to do this. And if no solution exists, state this. So we should check our answer to make sure that it's a good answer. It should be a good answer with the exponential function, but 2 raised to the 4 minus 1 equals 8. When I put in x is 4. 4 minus 1 is 3. 2 to the third equals 8, and that's true. Okay, so that's how you would do it if you have the Casio calculator. If you have a calculator that doesn't have base 2, then another way that you could do it would be to take the log of both sides. Your choice on this. And so when you do that, you take the log of this side, and you take the log, I wish I would have left some room, so I'm just going to scoot the 8 over. You take the log of this side. And then why you do that is that the property that allows you to move the exponent out in front is what I'm going to use. And so that was one of my properties of logarithm. So this is x minus 1 multiplied by log base 2 equals log of 8. And log of 2 and log of 8 are numbers, so you can find them. Log of 8 is not a nice number, so I don't want to get it yet. And log of 2 is not a nice number, right? So I don't want to use them yet. So I want to divide by log of 2. So when I divide by log of 2, I get x minus 1 equals log of 8 over log of 2. And then you can check to see if log of 8 divided by log of 2 is a nice number. Neither one of them were nice numbers, but when you put them together, log of 8 divided by log of 2, guess what? You get a nice number, you get 3. So since this is a nice number, you can use it. We get 3. If it wasn't a nice number, I would just leave it as this. Don't worry, I have one like that. It's coming. And then add 1 to both sides, and you get 4, and you would check the same way. So that's another way of solving the same problem. That's the recommended way of solving it if your calculator doesn't have log base 2. If my calculator didn't have log base 2, I would probably be going to Target to get a calculator that does have any base on it. The Casio calculator is so nice. Okay, this is not of the form, because remember the form you want it in is a base, an exponent, and then equals a result or a number over here. So 3 pieces is what I want. And I'm looking at it. I have the base, I have the exponent, but I have minus 65 instead of equals something. So I want to get it in the form. And once I get it in the form, then I'm going to solve it. So that's my strategy. And so what would I need to do to get it in this form? The base, the exponent, there's 3 pieces. And so I'm hoping that you're saying add 65. So when I add 65, I get 7.2 raised to the x. So that's the base and the exponent. And then on the other side, I get 65, and that's the result. And so now I'm ready. If you have a calculator that does any base, then what you're ready to do is you're ready to write it in exponential form. Now, this is an exponential form. You're ready to write it in logarithm form. So how you write it in logarithm form is the exponent equals the logarithm of whatever base, and then your result. So in our case, our exponent is x, so x equals, and then we need logarithm, and then we need the base, and the base is 7.2, which is an appropriate base because it just has to be positive and not equal to 0. And then the result is 65, which is an appropriate result because the result just has to be greater than 0. It can't be negative. And so, lucky for us, everything is perfect. And then we can put that in our calculator and solve for x. This is the exact value. I don't think it's going to turn out nice when I put this in my calculator. So this is the exact answer. So if they're asking for the exact answer, there it is. And they also wanted an approximation to 3 decimal places. So I'm putting in my log of any key, 7.2, and 65, and hitting equals, and I'm getting x is approximately equal to, and I'm supposed to take 3 decimal places, it said. So 2.114, the next number is a 5. There's 3 decimal places, and the next number was a 5, so that's going to bump this up, right? So we're going to get x equals 2.115, and put a box around that answer. And I should say squiggly equals, for it's approximately equal to this. And this is the approximate answer. Now you don't have to do it, you don't have to solve it differently just because your calculator doesn't have log 7.2 on it. You can just use the change of base formula. So from here, if your calculator didn't have it, okay, then what you could do is from here at x equals log base 7.2 of 65, you can just say that this is log of 65 divided by log of 7.2 using the change of base formula. And then you will get the same answer. Log is approximately 2.115. And so so you don't have to solve it differently. You can solve it differently. And so that's what your book recommends, is to solve it differently. If your calculator doesn't have that different, but you don't have to, you can use the change of base formula. It's a good idea to check your answer. And so I'm going to check my answer. So I'm going to put right in here. I wish I would have another piece of paper to check on because I wrote this over here. I don't know. I can check right up here. Check. So 7.2 raised to, well, I would like to use the exact value. I'll show you what happens if I use the approximate value. So that's log of 7.2 of 65 equals, minus 65 equals 0. So I'm going to see, I'm putting that in, and I'd like to use the exact value. So this is 7.2, and then I want to raise to, and then what do I want to raise to? Well, I want to raise to the log of 7.2 and equals 65. And then I want to take away 65. So I put the whole thing in my calculator, just like I saw it, and I hit equals, and I get exactly 0. If I put in the approximate amount, the approximate value, then it's not going to equal exactly 0, but it should be close. So let's try it using the approximate. So using the approximate, 7.2 raised to the 2.115, and then take away 65. And so I put in just the approximate value, and you notice that it's not exactly equal to 0. It's equal to 0.05163. This should be exactly equal to 0, like it was when we used the exact value. And the reason is because we used a rounded value. That was the reason that it didn't come out exact. And so when you check, you should check using the exact value, which sometimes is hard to put in. When the exact value is hard to put in, one way that you can do it, so remember the exact value was log of 7.2 of 65 was the exact value. I hit it equal, and that's my answer. So now if it's complicated to put in, this one's not real complicated to put in, but 7.2 raised to the answer. And so now I'm getting in that value, minus 65, and this ought to give me 0, which it does, because then I put in the exact value even though I didn't put it in. So this is a you try it. Pause the video if you want to try it. Otherwise, I'm going to do it with you. You notice that this is not of the form. This is what we're trying to get it in the form to look like: a base with one exponent and equals a result or a number on the other side. And so you can look at the pieces that are like what we are expecting. So the base is e, the exponent is negative x, and equals 9. All of those are part of the deal. But the 4 and the 5 are not supposed to be there. So do you have a way of getting rid of the 4 and the 5? And so that's what we're going to try to do. Then we'll be able to have it looking like this. Yeah, the 4 is add, so take away 4. So that's what we're going to do, take away 4. So when the dust clears, we get 5 e to the negative x equals 5. And it's not exactly like it's supposed to, but it's closer, right? It needs to have a base, an exponent, and the result. The base is e, the exponent is negative x, and the 5 is the result on the other side. This is 5 times e, and that 5 is extra. There is no 5 right here. There's no 5 out in the front. And so what we need to do is we need to get rid of that 5 by dividing by 5, because it's timesing. So you divide by 5. So now e to the negative x equals 1. And now I have got it in the form where it only has those 3 pieces. Those 3 pieces are the base, which is e, the exponent, which is negative x, and the 1, which is the result. And so now I'm going to write this in logarithm form. And so writing this in logarithm form, it would be the exponent equals the logarithm, the base, and the result. If you're saying it's never different, you're right, it's not. I've written it 3 times, right? I've written the formula for writing it from exponential form into logarithm form 3 times using words. So our exponent is negative x equals a log. The base is e. The result is 1. So we're going to see if log base e of 1 is a nice number. Now, I want you guys to know that this is natural log of 1, because that's what log base e is, right? So that is shortcut notation for log base e, just simply natural log of 1. So I'm going to use that on my calculator and see if it's nice. Natural log of 1. And so what does my calculator say that it is equal to? And it does. It says it's nice. It says it's 0. So that's nice. So I'm going to be able to put this as negative x equals 0. I'm trying to solve for x. So divide by negative 1. Silly, x equals 0. And I do like to check my answer. This is my last value. I'm going to check right here. So when I check my answer, 4 plus 5 e to the negative 0 equals 9. And you can put this in your calculator to check it. So, or you can do it by hand. 4 plus 5 raised to the negative 0. So I put that in, and I'm expecting the answer to be, what did I forget? Oh, I forgot the e. Sorry. 4 plus 5, and then times because I forgot to put the E, and then raised to the minus 0. And I do get 9. I wasn't getting 9 before because I was talking at the same time that I was putting it in. And so I forgot to put in the E. And so I got a different answer, and because I didn't put in what I had. Okay. Now this one here, there's another way that you can solve it on this particular one. And so I'm going to show you that way. And I'm going to show you how to solve it using the logarithm approach as well. This one's pretty complicated to solve on the logarithm because it's got exponents on both pieces. And that makes it more complicated to solve. I'm even thinking about how I would get it with exponents on both pieces. It's more complicated, definitely. But when you have exponents on both pieces, if you're able to notice that the bases are the same, 27 is 3 to the third, and 81 is 3 to the fourth. So they have been kind of working with us with our number sense. And so if you can notice that they're the same, then 27, that's 3 to the third raised to the x. And 81, that was 3 to the fourth raised to the 2x minus 3. And then remember the power rule that says you multiply those exponents. So this is 3 to the 3x equals, and then when I multiply these exponents, it's 3, and then 4 times 2x is 8x, I'm distributing, and 4 times 3 is 12. And notice that both sides have base 3, and that's what this property is saying, that if both sides have the same base, which I only noticed that they had the same base and then made it happen. I didn't really do that, right? I mean, as far as I just noticed it was true and took advantage, then you can set the exponents equal to one another so that this would become 3x, that's the exponent, equals 8x minus 12. And then I can solve that for x. So I can take away 8x both sides. Negative 5x equals negative 12. And then dividing by negative 5, I get x equals 12 over 5. And there's no reason to write that as a decimal. It says to, if appropriate, to write it as a decimal. And they're wanting a complicated logarithm to be written as a decimal. This one doesn't even go 3 places. 12 divided by 5 is only equal to 2.4. So if you wanted to write it as a decimal, yeah, go ahead. It's equal to 2.4. So this is the exact value, 12 over 5. And 2.4 is also the exact value. And so I didn't have to round. And so it wasn't something that was that needed to be rounded. And so anyway, so that's how you would solve one like that. I think this would be very complicated to try to write as, to try to do with a logarithm. Because a logarithm, it's hard to get it in the correct form where you have just one exponent because you have exponent on each side. Anyway, so I'm not going to worry about doing that. I don't feel that good, and so we'll call it that. We have one way of solving it. We'll call it good enough. Then there's some formula problems, and there's the compound interest formula, where A stands for the amount in the account after T years. P stands for the principal invested. 1 is just the number 1. R is the interest rate written as a decimal. N is the number of compoundings per year. And N is again repeated, the number of compoundings per year. And T is the number of years. So this is if you're going to compound 12 times a year, that would be monthly. 4 times a year, that would be quarterly. 365 times a year, that would be daily. I'm trying to think of, something else. Semi-annually would be twice a year, N would be 2, right? If you compound continuously, then the formula is A stands for the amount in the account, P stands for the principal invested, E is Euler's number, 2.71718, however it goes. R is the interest rate written as a decimal, and T is the number of years. So this is compounding more than 365 times a year. This is compounding more than every minute, more than every second in a year. So we're going to give a try to some problems here using our formula. I'll write out the formula and we'll use it. It says, suppose that you're going to invest $100. So this $100 is the amount that we're going to invest, and that is called the principal. So we're going to name that to be P. And then the 1.5% is the interest rate. So this is the interest rate, but I need to write it as a decimal. So as a decimal, this is 0.015. And so it needs to be written as a decimal. So those are the things that we've seen so far. And it says, how much money would you have? Now, how much money you would have is A. That's A. After 10 years, that's T. Hello, my friend. I'm just finishing up a video for my algebra class. And so if the money was compounded monthly, now compounded monthly is our N, and our N here monthly, there's 12 months in a year, is 12. So what we're going to have for our formula is A equals P times 1 plus R over N multiplied by T. So in our case, our P was 100. 1 is part of the formula. The interest rate, not very much, 0.015. And divided by N, which is 12. And then times 12, N times T, and 12 times 10. So some calculators don't like the 12 times 10, and so that's 120, so put in 120. My calculator will handle the whole thing. Just put it in just like you see it, and that will give you A. And so 100, parentheses, 1 plus fraction 0.015 divided by 12. End of parentheses, so I'm putting it in just like I see. I want the raised to key, and I want 12 times 10. And long story short, after 10 years, I'll have $116.17. The next number is a 2, and this is money, so you should round appropriate to money. So this is rounded appropriately is $116.17. Seems like I should have more than that after so long of having the money in the account, but it's because the interest rate was so low. How long would it take to double your money, grow to $200? Well, we know it's going to take longer than 10 years, because in 10 years, we only had $116. If your money is compounded quarterly, and so this is even less compoundings. So this is just to practice. So this is giving N is 4, compounded quarterly. So we have our formula, A equals P, 1 plus R over N, and then NT. So A is known, it's 200. P is known, that's 100. 1 plus, the interest rate was 0.015, so that didn't change. What did change was N. They said use 4 for N instead of compounded monthly. And then 4T. And what we're trying to solve for is T. And so this is the base right here. That's the whole base. and the 100 is extra, because remember how we want our things in this looking like this: a base, and then an exponent, and then equals a number. And the 100, this is the base right here. That's the base. I'm putting a box around it. This is the exponent, 4t. The 100 is extra. It's not the base. And so what we want to do is we want to divide by 100. Where did those other problems go that I knew I had? Oh, I might have, I don't know. 2 equals, and then I'm going to write this base just as a nicer base. So it's 1 plus 0.015 divided by 4. And so it's 803 divided by 800, which is 1. So since I don't have to round, I'm going to be able to write the whole thing. You don't want to round on these for certain. Okay, so now I'm going to write this in log form. So in log form, you do your exponent equals your log, and your base, and your input, right? So our exponent is 4t, our log, and our base is this awful 1. And so it's not allowed to be 1, and this number is not exactly 1, right? This number is a little bit bigger than 1. And then our input is 2 because of the doubling. And this is not going to be a nice number, and we're trying to solve for t. So all we would do is divide this whole thing by 4. So this will be the exact value. I didn't go ahead and put that in my calculator. I'm dividing by 4 here because I knew it wouldn't be nice. So input 2 divided by 4. And then I'm going to, it said to round to the 10th. And so I always follow whatever rounding it had. So I'm going to have here my fraction, my log any base, and the base is 1.00357 of 2. And then the whole thing divided by 4. Oops, that didn't get down there in the bottom, divided by 4. That's why I like to see what I put in. And so this is 46.29 to the 10th, though. That's the 10th spot. So the 9 makes that a 3. So this is, rounding appropriately, 46.3 years, believe it or not, for that money to double. Yeah, that's not a very high interest rate. How long would it take to double your money if your money was compounded continuously? So instead of compounded monthly or compounded quarterly, this is the last problem, my calculus students, thank you, I'm so sorry. Then we have A equals P E R T. So we started with, we wanted to end with $200. We started with 100. Our very small interest rate was 0.015 and then t. So again, we don't have it in the form. We need to divide by 100. So we get 2 equals e to the 0.015t. And then this is our base, our exponent, and our input. So our 0.015t is our exponent. So just following our writing it in log form, right? So that is our exponent, equals our logarithm. Our base is e of 2. And that is the same as the natural log of 2. So this is 0.015t equals the natural log of 2, if you want to have it like that. The natural log of 2 is not a very nice number. You would divide by 0.015, so that t equals, this is my exact answer, the natural log of 2 divided by 0.015, and then that is approximately, and then that'll be the end of this video. So fraction, natural log of 2, so I'm putting it in my calculator, end, and divided by 0.015 equals, and we're getting 46.2 years. And so the next number was a 0. So it doesn't shave off very much time to have it compounded continuously. So that's the end of this video, my friends. So I'm going to push stop if I can figure out how to push stop recording.